Welcome to this video about gravity. This is the fourth in our series of gravity and circular motion, the first in our series for gravity. This video is actually pretty straightforward. We have been talking about circular motion, and we've been talking about this idea of having weight, but we also know that gravity is a force that exists everywhere in the universe. And gravity will exist between any two massive objects, that is, objects that have mass. So if we have two objects, object 1 and object 2, gravity will pull them together. So there will be a gravitational force of attraction. Let's call this one 1 and this one 2. There will be a gravitational force of attraction on this one, force from object 2 on object 1. And this thing, this object over here, object 2, will also have a force from object 1 on object 2. And they will pull toward each other with equal amounts, because that's what Newton's third law says, right? That they will, that a force from one object on a second object is equal to a force from that second object back on the first object. So gravity is an attractive force. That is, that gravity will only pull things together. It never pushes things apart. And Isaac Newton actually did a lot of work on things past his three laws of motion, of dynamics, in fact. And he did a lot of work with his universal law of gravitation, is what it's called, universal law of gravitation. So Newton's universal law of gravitation is the equation that we're going to learn today. And if you can imagine, we know that the force here, this force here, is going to increase as this object gets bigger. As m2 gets bigger, we know that the force will increase, because let's imagine if this was the Earth, right? Let's imagine object 1 is the Earth and object 2 is a person. The bigger the person, the bigger the gravitational force of attraction, that is, the bigger the weight. So F will go up as m2 goes up. We also know that F will go up as m1 goes up, because think about it like this: if we were to stand on a more massive planet, like say Jupiter, that planet will pull us more than Earth will, because Jupiter, I think, is roughly 1,000 Earths, maybe more. So imagine if we had, instead of just one Earth, if we had 1,000 Earths pulling us, that would be quite significant. So F will increase as both masses increase. We also know that as we get farther away, F is going to decrease. So F will decrease as our radius increases. Now, what do I mean by the radius? Well, if I were to draw this object here at the center of a giant circle, so let's do it like this. If I were to say that this object here was at the center of this circle, then the r that I'm talking about would be this distance from here to here. So we'll call this quote-unquote r. And that r is really just a distance. It's the distance between these two objects. I call it a radius because that's how I learned it, and that's how I have seen it many times. You can call it a d if you would like. It will be on your equation sheet as an r. So we know that as the radius increases, as it gets farther away, our force will decrease. I've said a few times in class that if we were standing on the top of Mount Everest, we would feel ever so slightly lighter than if we were standing at the bottom of the deepest valley on Earth. So Death Valley, I don't know if that's actually the deepest valley, but we would feel ever so slightly lighter at the top of Mount Everest than we were at any lower point. That is because of this idea that as we get farther away from the center of our object that is creating a force of attraction, or the second part of our object that's creating force of attraction, then we will get a smaller force. Okay? Now this all comes together to come up with Newton's universal law of gravitation, and it looks like this. F gravity, so I'm going to call it F12. Well, let's just call it actually Fg. So the gravitational force of attraction between objects 1 and 2, we know is going to increase as m1 increases. So that means that we will have an m1 on the top. We will have an m2 on the top. And we're going to have an r on the bottom. Now, because it doesn't matter which reference frame we think of, if whether we are M1 or we are M2, the only way that we can do that is with an addition or a multiplication sign, and it turns out that it is a multiplication sign here. The force of gravity is proportional to the product of the masses, M1 times M2. Now, the other change is that the force of gravity actually gets bigger, or sorry, it gets smaller, not with the inverse of the radius, but with the inverse square of the radius. That means that as we get farther away, it has a squared effect on the size of our gravitational force. So this is the rough equation that we've got here, and Newton found that this was not giving him the exact forces that he wanted. So there's a coefficient out in front called capital G. Capital G is the universal gravitational constant. So we're going to call this the universal gravitational constant. Universal grav constant. And it has a set value. This is the value that Newton uncovered. Actually, I believe that Kepler uncovered it as he was going through. And the universal gravitational constant is equal to this amount, and it is 6.67 times 10 to the negative 11th. Go ahead and pause the video right now and see if you can figure out what the units for G are going to be. Welcome back. Hopefully you saw that the units for G are based on M1 and M2 having to cancel out our masses, and R squared on the bottom having to cancel out our distance here, and needing to have newtons left over. So our units for this are Newton meter squared per kilogram squared. Because if we plug this in, it's going to cancel out all of our units. All right, so let's try a problem. If we have 4-point masses in the orientation below, and here I'm going to draw the orientation, we're going to have the orientation something like this. Draw all the gravitational forces that exist in the orientation. So let's start with the upper left-hand corner. This one is going to have a force this way from this one. It will have a force this way from this one, and it will have a force this way from this one. Similarly, we're going to have a force up here, over here, and across this way. This one will have another force this way, and a force this way, and a force this way, and this one will have a force here, and here, and here. And now we can see that some of these are going to be equal. Like, for instance, this one will be equal to this one. This one must be equal to this one to this one, and this one to this one, and then also this one to this one, and this one to this one. So lots of pairs of equal forces here. Remember, these are all forces of attraction. They will never push away. They will only pull toward each other. Let's try another one. We have a girl named Brandy, whose mass is 42.5 kilograms, sitting 1.5 meters from a boy, George. There you go, boy George. 63 kilograms is his mass. What's the force of gravitational attraction between them? So we're going to have Brandy sitting right here, and George will sit right here. So Brandy and George, and we are going to say that the distance between them is 1.5 meters. Her mass is 42.5 kilograms, and George's mass is 63 kilograms, and we're asked to find the force of gravitational attraction. Well, we know, according to Newton's universal law of gravitation, that the force of gravity between them, Fg, is going to be equal to G times m1 times m2 divided by r squared. Now here's where a lot of people get in trouble, is they want to say the r is half of this distance. But remember, we're putting one of these people at the center of a circle. So I'm going to put Brandy at the center of the circle. And now George is at the outside of the circle, so our radius is 1.5 meters, because that's the radius of the circle. So Fg is going to be equal to 6.67 times 10 to the negative 11th times the first mass, 42.5 kilograms, times the second mass, 63 kilograms, divided by the distance between them squared, so divided by 1.5 squared. As you go through all of that and you simplify, you should end up with the force of gravitational attraction between them being 7.94 times 10 to the negative 8th newtons. The force of gravitational attraction between them is 7.94 times 10 to the negative 8th newtons. Now think about it like this. 10 to the negative 8th newtons, that's a very small amount of force. When you consider that humans, on average, are let's take a look at Brandy, for instance. Brandy has a mass of 42.5 kilograms, using roughly 10 as our gravitational acceleration constant. That means that Brandy is pulled down with 425 newtons of force. 425 is 4.25 times 10 to the second, which is 10 to the 10th more than this gravitational force of attraction between her and George. So this right here, this is a very small amount of force. In fact, it's so small that without specifically trying to measure it, without designing a specific apparatus to measure this, we cannot feel this. You will not feel the gravitational force of attraction between you and some other person. The final question is, if you weigh 567 newtons on Earth, how much would you weigh on Mars? And if I were to ever give you problems like this on a test or a quiz, I would give you a table like this one right here, which gives the mass of the planet and the radius of that planet. So we know if we weigh 567 newtons on Earth, using the fact that weight equals mg, that means that the mass of us is equal to 5.67 kilograms. All right, now we can only use this equation because we know what g is on Earth. If we didn't know what g was on Earth, we would have to do something slightly different. And we would have to then use the fact that the weight is the gravitational force, which is equal to 567. So on Earth, what that means is we are saying 567 equals g times your mass times the mass of the Earth, divided by the distance between you and the center of the Earth square. Now remember, this is between you and the center of the Earth. That's where the radius of the planet comes into play. Because if you stand on the surface, the distance between you and the center of the Earth is the radius of the Earth, roughly. So doing this, if you were to go through this, you would get something close to 5.67. You would likely get something slightly bigger because I used 10 up here for gravity instead of 9.8. So if you were to do that, you would plug in the mass of Earth for right here, and you would plug in the radius of Earth for right here, and you would be solving for your mass right here. For now, we're going to use the mass of 5.67 because it makes it a little bit easier for us. So then you would go back and you would say that my weight on Mars is equal to the force of gravity on Mars, which is equal to g times your mass times the mass of Mars divided by the distance between you and the center of Mars squared. So when you do that, this means it's equal to 6.67 times 10 to the negative 11th times your mass, 5.67, times, and I'm running out of space here, so I'll jump to the next line, the mass of Mars, which is 6.42 times 10 to the 23rd. And we're dividing that all by the distance between you and the center of Mars squared, which is 3.4 rounded times 10 to the 6th, and that whole thing is squared. And when you do that and you simplify, I think if you use 5.67, you won't get this number, but if you use this mass that you correctly solve for down here, you will get this. You will get 218 newtons, roughly. If you got something slightly different, remember I used, for calculating this, I used this mass. But if you use 5.67, you will get something slightly smaller than 218 newtons. But think about it like this. If you weigh 567 newtons on Earth, on Mars you weigh 218 newtons. That means that you are half as heavy on Mars as you are on Earth. That's it for now. Next class we're going to find how to calculate the acceleration of gravity on a planet, and we're going to start to talk about Kepler and his laws of planetary motion.